Hi, and welcome back to Allen High School. We are discussing electrochemistry at the AP/IB/HL level. Now, we left off our conversation discussing the standard hydrogen electrode, the electrode against which the tendency to gain or lose electrons is measured. So let's take a look at how it is designed. Now, hydrogen is a gas. Our half reaction here, you notice, does not have a metal associated with it. So our electrode needs to be something that is non-reactive. We don't want the electrode reaction to interfere with this reaction here. So we need non-reactive electrode. And an expensive but good solution is to use platinum. So you notice we have the platinum wire. It's part of the electrode. It's the way we conduct electrons, but it is not showing up in our half reaction. Another type of non-reactive electrode that is used is to use graphite. That's an allotrope of carbon that has alternating double bonds and so allows the conduction of electricity. So we've got our hydrogen electrode here. We have to have a way to provide the gas. You notice it's at 1 atmosphere because we are discussing a standard. We have to have a source of H+. You might want to use hydrochloric acid. Probably not nitric acid because nitric acid in the presence, nitrate in the presence of acid can actually react. Not when it's in the presence of salts by and large, but when there's acid present, it will react. So we're not likely to use nitrate, but hydrochloric acid would be a good alternative. So here's our platinum wire. Here's the platinum electrode, the surface. On this surface is where we're going to have our hydrogen gas, and depending on our other half reaction, what our other half reaction is, if it has a greater tendency to reduce, that means our hydrogen has to be oxidized. Okay, so in this case, we would have hydrogen being oxidized, releasing electrons and releasing H+ into our system. If our other half reaction has a greater tendency for oxidation, so we're talking about the other, what we've hooked this She up to, well, then hydrogen's going to be reduced. So it's going to grab onto those electrons and form hydrogen gas. And so that's what we would be seeing in our half reaction. Now, if it was being reduced to form hydrogen gas, we're going to see bubbles. So that would be our evidence of our chemical reaction. Now let's take a look at the table that has been compiled for this. So let's zero in on that hydrogen. Now we're going to be talking about relative potentials relative to the hydrogen, the She half reaction. And so we define that as 0. It's not a physically meaningful number. It's going to be a relative number. Now, if you have a standard reduction potential table and you forget that it is the more positive that wants to be reduced, maybe it would help you to remember that fluorine is the most electronegative element on the periodic table. And so shoot for fluorine. Be careful. This is not always at the top of the table. It's important that you know that the more positive one wants to be reduced. The more negative one wants to be oxidized. And hopefully it makes sense to you that our alkali metals would be down there because our alkali metals have a great tendency to give up electrons. It's a negative thing for them to gain electrons. Okay, for fluorine likes electrons. It's a very positive experience for fluorine to gain those electrons. So, as it becomes more positive, it wants to be reduced. As it becomes more negative, it wants to be oxidized. So that's how we would compare ours. Okay? Now, let's take a look then at two terms that we haven't talked about yet, but they're used quite frequently on our MSDS sheets. We, often they'll say, whoa, be careful, strong oxidizing agent, sometimes called an oxidant. Okay, now let's take a look at how that would play out on this chart. As the more something wants to be reduced, the better oxidizing agent it is. So it's kind of the opposite, right? If it wants to be reduced, it'll take electrons. By taking electrons, it helps something else be reduced. So that's how we get that term. So they're opposite one another, and they're always reactants. Now, as we go the opposite direction, the more it wants to be oxidized, the better reducing agent. Whoops, I can't spell today. The better reducing agent it is. So the more it wants to be oxidized, the better reducing agent it is. So hopefully you are capturing those ideas. Now, in the media, you may hear about certain vitamins or skin creams being antioxidants. Well, that means they're trying to react with these oxidizing agents so those oxidizing agents can't oxidize our cells. So that would be another way you would hear, another time you would hear those terms used. Okay? Now, let's go back to our discussion of lead and chromium. And of course, I would grab tables that don't have lead and chromium on them. So I'm going to give you those values here as we talk about our non-spontaneous, whether it's non-spontaneous or spontaneous. The lead reduction potential, I need someplace to write it. I'm going to write it here. So I'm still talking about A right now. I just need room, and we'll talk about this later. Our lead reduction potential, lead 2 plus 2 electrons going to lead, that potential is minus 0.13. Our chromium 3 plus 3 electrons is actually a negative 0.74 volts. So remember, we want our most positive to be reduced. This would be what would happen in a spontaneous situation. And we want our most negative to be oxidized. So that would be spontaneous. Unfortunately, in our cell, we have this being oxidized and our chromium being reduced. So in the cell we designed, we have it occurring opposite of what would be spontaneous. I usually figure out what things want to do spontaneously. If they're doing that, great. If they're doing the opposite, we now know we have a non-spontaneous cell. So let's take a look then at how we could actually mathematically determine this in our next video, because we now know we set up a non-spontaneous situation. So let's go on to calculating it in our next video. Until then, this is signing off.